Good afternoon, students. Welcome to today's session. So we will complete hydrodynamics today. Last time we had looked at the derivation of Bernoulli's equation. So we'll start straight away with applications of Bernoulli's equation in fluid dynamics. With that, we'll complete this section of fluid mechanics hopefully today. Okay, so let's begin. Just a moment. Right. So having understood the concept of streamlined motion or steady flow of an ideal fluid, we had derived the two mathematical equations that are applicable for such type of motion, that is steady or streamlined motion of an ideal fluid. So we'd seen continuity equation is completely based on the property of the ideal fluid being incompressible, okay, and therefore overall mass and volume conservation as it flows through in steady motion or streamlined flow. So we have a cross section of area A1 where the velocity of flow is V1 in magnitude, and we have another cross section of area A2 where the velocity of flow is V2 in magnitude. So we had seen, in keeping with steady flow or streamlined motion, the fluid maintains a uniform volume flow rate, which we can think of as dV by dt, as area of cross section into velocity. Okay, so therefore, at any two arbitrarily chosen points, A1 V1 will be equal to A2 V2, uniform or constant. Okay. So this is two ways of expressing the continuity equation. Either we express it as a generality that A into V is uniform, or A1 V1 is equal to A2 V2 at any 2 points. Okay. And then we also saw that by applying a sort of work energy theorem kind of application, if with respect to some horizontal reference level, the heights of these two sections, the average heights are H2 and H1, and the hydrostatic pressure of the fluid, or basically the absolute pressure, whatever we say, as P2 and P1 like this respectively, at the position of these two cross sections, then we can relate the pressure difference with the height difference with the difference in kinetic energy per unit volume by expressing it like this, that P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2. So this was a Bernoulli's equation, or another way of expressing it, that at any given point inside the fluid, the sum of three scalar quantities, pressure, half rho V square, which is kinetic energy per unit volume, and rho GH, which is like gravitational potential energy per unit volume, with respect to this reference level, that is constant or uniform. So these were the two mathematical equations. Now let's start looking at the application of the same. So for example, if we have a situation like this where we have a horizontal pipe which is kind of tapering like this, and we know that this cross-sectional area is 6 centimeters square, whereas this cross-sectional area is 2 centimeters square. Now, if a liquid is flowing through like this, the flow velocity is v1 here and v2 over here. So given that water flows in steady flow, such that v1 is equal to 1.6 meters per second. Okay. Density of water as usual is 1 gram per cc. So find V2, very simple. The volume flow rate is delta V by delta T or dV by dt, whatever. Okay. And third, we have to find the pressure difference P1 minus P2, where P1 is pressure at any point at the cross section A1, and similarly P2 is the pressure at any point at the cross section of area A2. Just work this out numerically quickly. Yes, very good, Naman, that's correct. Snikita, correct, very good. Yeah, just have to be a little careful about the units. Okay. So remember, the area of cross section is given to you in centimeter square, whereas the speed of flow is given in meter per second. So be careful when you're converting to volume rate of flow. So obviously the first one is continuity equation, A1 V1 is equal to A2 V2. So A2 is 1/3 of A1. So that means V2 will be 3 times V1. So V2 should become 4.8 meters per second. Okay. Now also this area into velocity of flow is the volume rate of flow. Okay, so the volume rate will become, like, one way to express it is 6 centimeters square into 1.6 into 10 raised power 2. We convert this to centimeters per second. Okay, so that will become 9.6 into 10 raised power 2 cubic centimeters per second. So that will be the same thing as 9.6 into 10 raised power minus 4 meter cube per second. Or you can even see that that is 0.96 liters per second, because 10 raised power minus 3 meter cube is 1 liter. Right. So that becomes especially important when we are looking at the pressure difference, because we want the pressure difference in pascals. So when we apply Bernoulli's equation, so this is a general form of Bernoulli's equation. But here we'll see that H1 is equal to H2 because it's a horizontal pipe. It's a pipe in a horizontal plane. Okay. I mean, there might be slight minor difference of height between, let's say, a point like this and a point like this. But if you consider the streamline going through the midpoint, to the central axis of the pipe, that's in a horizontal plane, right? So that height difference is 0. Okay. Whereas V2 and V1 we see V2 is greater than V1. So P1 will become greater than P2. So P1 minus P2 will be a positive quantity. So when we calculate this, so this will be in pascals. That's 500 into, I can take 1.6 square common. Should be a fairly easy calculation to do. So this is the pressure difference. Okay. Now we've already understood why P1 is greater than P2, because as a fluid element is going across this section, you can see that it's accelerating. Okay. So the force due to pressure from this side should exceed the force due to pressure from this side. Logically. So hope the units and everything are clear and matching for everyone. Yes. Okay. So you can also convert it to atmospheres, but we'll just leave it here as 1.024 into 10 raised to 4 pascals. So something in the order of magnitude of about 0.1 atmospheres. That's the pressure difference that is created because of the flow of the liquid like this. Okay. Okay. So for example, that day we were discussing about logically how the pressure variation should occur in a vertical pipe which is of uniform cross section. So today we can see how Bernoulli's equation will actually help us calculate the exact pressure difference. And we'll see something very interesting, that when liquid moves in streamlined motion across a vertical pipe of uniform cross section, it doesn't matter whether the liquid is flowing directionally from top to bottom or bottom to top. Okay. The pressure difference in such a situation will be the same as the pressure difference would have been in a static column of liquid. That is, 2 points separated by a vertical height of h will again have a pressure difference of rho gh. And it's not entirely surprising when you think in terms of work energy also, why that's going to happen. So firstly, you can see here that area of cross section is uniform. So velocity of flow will also be same. But now if you compare the pressures at two such points like this, which are separated by a height of h, now you can see that P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2. Now this time you can see that B1 is equal to V2 because A1 was equal to A2. Okay. But H1 is equal to H2 plus H. The height of this point is more than with respect to any reference level. So we can see that rho G H1 minus H2 is equal to P2 minus P1. So the pressure at the lower point exceeds the pressure at the higher point by rho GH. So this is the same result as a static column of height h. Okay. But of course, that is only this case. Okay. If the cross section is variable, then that will not be happening. So if this is A2 and this is A1, and this height difference is h, then That will not be the case. V2 will be less than V1 in this case. So here you can see that P2 minus P1 will become rho G H. Okay. So you can see that in this case, because of this, P2 minus P1 will be greater than rho GH in this situation. Okay. The same thing if it had been like this. The above point is of smaller area and the lower point is of larger area. Wait, I should just wait a minute. I think I've got this one wrong. Speed is decreasing as it's going up. So this should be reverse. This I should get P1 minus P2. But remember here I've taken the lower point as 1. Upper point as this. So P1 minus P2 actually become rho GH plus half rho V2 square minus V1 square. Now this will be a negative quantity. Because V2 is greater, V2 is less than V1. So from this you can see that P1 minus P2 here is less than rho GH. Okay. Whereas in this case, if the pressure here is P1 and the pressure here is P2, P1 minus P2 will be greater than rho GH. In fact, like this, where V2 is greater than V1, so it's positive quantity. Okay, so hope these examples are clear. Okay. Now moving on, one sort of standard application which is used for a device called the Venturi meter. It is a simple apparatus used to measure the volume rate for steady flow. Consider pipeline through which fluid is in steady flow. So what you do is you have an attachment in between called the Venturi meter. which is used to measure the volume rate of flow. So the attachment in between will have sort of tapering of the pipeline like this. And also at two appropriately selected points, sort of narrow capillaries like this will be inserted. What will happen is that as our liquid is in steady flow, like this, the pressure of the liquid will drive a vertical column of liquid in each of these capillaries, but we'll observe that the vertical column will have a height difference. And that height difference is going to be related to the difference in pressure at this point, let's say 1, and this point 2, or the difference in flow velocity at these points 1 and 2. So if we know the area of cross section here is A1, area of cross section here is A2, and for example A1 is equal to n times A2, where n is a number greater than 1. Then by applying Bernoulli's equation, we can see that since H1 is equal to H2 at these 2 points, okay, at points 1 and 2. So P1 plus half rho V1 square is equal to P2 plus half rho V2 square. So this is just like the application question that we had done, that numerical problem. Okay. Now, next step, when we employ continuity equation, that tells us that V2 is equal to n times V1. So P1 minus P2 is equal to half rho. In fact, what we can do is we can write this as, let's say, Q, which is the volume rate. So we can write V1 as Q by A1, and we can write V2 as n times Q by A1. So it becomes like this. Now this pressure difference is also equal to rho GH, where H is the difference in the level of water present in the columns. So this is considering the vertical gradient. In the two capillaries. Okay. So left hand side of this equation. So basically, we can say like this. This is our equation 1, which is coming from Bernoulli's equation. This is our equation 2, which is coming from continuity equation. And now we have this other equation also, which is coming from vertical pressure gradient. So considering all this, we can see that rho GH is equal to half rho Q square by N square. sorry, q square by a1 square into n square minus 1. So provided thing that we have measured in the experiment, so we know that n is a quantity that is known, A1 is a quantity that is known. That means we have measured the cross-sectional area, we measured the ratio of the cross-sectional areas of A1 and A2. So from that, we can now back calculate the volume rate of flow is becoming square root of 2gh into A1 square upon n square minus 1. Q here is dV by dt or the volume rate. We get this kind of a formula, okay, for the given Venturi meter. So a standard instrument will have a standard value of A1 and N. Okay. And by just measuring the height difference for the flow of liquid going through that particular Venturi meter, we can calculate the volume flow rate through that particular Venturi meter. So, typically the Venturi meter is like a contraption, which is, let's say, from here to here. So whatever is the pipe through which our liquid is flowing, we sort of break the pipe at these two places and clamp the Venturi meter in between. And as liquid passes through, we can continuously measure the volume flow rate. So of course, if the velocity of liquid flow becomes too large or the volume rate becomes too large, then we lose the property of steady flow, and there is what we call turbulence. And later in properties of matter, we'll see there's a calculation of something called Reynolds number for the flow. So the Reynolds numbers value tells us whether or not we can get away with applying the steady flow motion concepts, or turbulence is becoming too strong a factor for our analysis to be correct. Okay. So as long as the liquid flow is not, it's reasonably non-turbulent. Okay. Obviously, nothing will be an ideal exact steady flow, but as long as there is not too much of turbulence, this is going to give us an accurate measurement of volume flow rate. So this is something part of your fluid mechanics syllabus. So you should know the apparatus by name, that this is the instrument called the Venturi meter. This is how it functions. So that if a question directly refers to the Venturi meter's parameters without giving you the diagram or without describing the whole experiment, you should know what they're talking about, right? Okay, now next on to another standard application of Bernoulli's equation. Now notice that whenever we use Bernoulli's equation, it is always sort of in association with continuity equation. So that will typically happen for any physics problem. Okay, Bernoulli's equation is rarely used isolated as a single equation. Always in any numerical application, you will have to simultaneously use the result from Bernoulli's equation and continuity equation. Anyhow, so next thing we'll see is what is called velocity of efflux. So this is a typical situation where we have liquid in a tank, okay, or in a vessel. It can be an open vessel, it can be a closed vessel with a seal at the top also, it doesn't matter. Okay, but the important thing is if there is a small opening, typically small opening is given a specific name, it is called an orifice. So if there is an orifice at, let's say, near the bottom, then the speed with which liquid comes out of it, the velocity of efflux or speed of efflux. So this kind of an opening is called an orifice. An orifice is basically a very small opening, small aperture or opening. Then from here liquid will be gushing out. So the speed with which the liquid comes out, that is called the velocity of efflux or speed of efflux. Outflow. Of fluid. So here what happens is we visualize these streamlines like this because the entire body of liquid is flowing down. So the surface of liquid will also be coming down. Okay, so we assume there is some speed here and the cross sectional area is A and the orifice is of small aperture of area, let's say small a. So basically small a should be extremely small compared to capital A. A typical example would be capital A is, let's say, of the order of magnitude of meter square and small a is of the order of millimeter square or something. So that's typical example of the orifice, that A by A is order of magnitude 10 raised by minus 6 or less, that kind of situation. Then it qualifies as an orifice. Okay. So now what we do is we take a point over here as our first point and a point just outside the orifice as our second point. And we apply Bernoulli's equation and continuity equation in simultaneity. So taking these 2 points, you can see the pressure at the first point will be equal to pressure at the second point will be atmospheric pressure because one is on an open surface, two is just outside the tank. So the pressure at 2 is the atmospheric pressure. So now V1 is equal to V, V2 is equal to the efflux speed. Now capital A into V is equal to small a into VE. So we can see that V is equal to this. Okay. So you can see that V itself is going to be very small compared to VE because A by A is very small compared to 1. So now, so this is our continuity equation already used. Now Bernoulli's equation, In this, we can see that P1 is equal to P2 equal to atmospheric pressure. H1 minus H2 is equal to H. And V1 is equal to V, which is this much, and V2 is equal to our efflux velocity. So applying these parameters here, we'll get rho GH is equal to half rho efflux velocity square into 1 minus E square by E square. So the proper formula for efflux velocity becomes square root of 2GH divided by this, but we can also approximate this as. So interestingly, it is when we take a proper orifice so that we can take small a by capital A to be extremely small compared to 1, then we can take the efflux velocity equal to rho GH, square root of 2GH, which is like the free fall speed through a height of h. So this is the speed of efflux through an orifice in a tank. There is a general expression would be the one written on top, square root of 2GH divided by that factor. But the moment we are talking about an orifice, okay, that factor becomes 1, because a by capital A is very small compared to 1. So again, this is a standard application and you should memorize the formula, which is actually very easy to keep in mind because it is same as the formula of free fall. Okay, we also hope this derivation is clear. Now let's look at a standard, or rather not a standard. Let's look at a small variation of this type of problem. So in this, we have a tank with an orifice, but the tank is filled with a combination of two fluids which are non-miscible. So there is water up to a certain level, and above water there is floating a layer of oil. This is oil, which has a density of 0.8 gram per cc. This is water, which has a density of 1 gram per cc. Okay. Now the oil layer is of height h1, let us say 12 meters. Okay. And the water level is of h2 at the moment, which is, let's say, 15 meters. We'll take G as 10 meters per second square. And there is an orifice over here. So water is gushing out. So we have to find the speed of efflux for water. So just try out this question. Okay, so we'll discuss this in Yeah, students, sorry, there was some connectivity issue at my end. Am I audible to all of you now?
Yes.
Okay, okay. Yeah, so let's continue. So yes, this speed will be something in the range of, I think, around 22 meters per second. Anyhow, so let's first understand the question numerically. So it's not too difficult, but one thing you just have to understand technically, that Bernoulli's equation can only be applied to streamlines which are across one particular liquid. So I cannot apply directly Bernoulli's equation between a point right at the surface at the top over here, where I know the atmospheric pressure is P naught and this. So what I'll have to do is I'll have to relate one point here with another point here, with finally a third point here. Now this second point I can take ambiguous. I can take it at inside the oil also, or I can take it just below the interface inside water also. Okay, so if I relate 2 and 3, I can see that pressure at 2 plus half density of water into some V square, okay, plus density of water into G into H2 should be equal to pressure at 1, or rather pressure at 3, which will be, by the way, atmospheric pressure, plus half density of water into efflux velocity square. Okay. So I can say that P2 plus density of water into G into H2 is equal to P naught plus half density of water into efflux square minus V square, where I can approximate this as efflux velocity square. Okay. So I have this equation. This is equation number 1. Okay. Here the only thing I've done is I've neglected V square with relation to, so if this is V, I've neglected V square compared to efflux velocity square because it's an orifice. Okay. Now again we can come to points 1 and 2. So we can see that P1 plus half density of oil into V square plus rho into density of oil into G into H1 is equal to P2 plus half rho density of oil V square. Okay. And P1 is equal to atmospheric pressure. So we can see that P2 is equal to atmospheric pressure plus density of oil into G into H1. That becomes our second equation. Now we'll substitute this in equation 1, and that's how we'll see that it's okay. So our efflux velocity in parametric form will come out to be 2G into H2 plus relative density of oil into H1. So this kind of thing. So 15 plus 9.6, so that is that kind of quantity will come out to be. So but this is the proper answer in parametric form. Okay, so hope this is clear, people. Yes, that's a very interesting thing, Aman. You can do that. So Aman is pointing out that we can convert this to an equivalent problem where we replace the oil layer with an equivalent amount of water which would apply the same pressure. Okay, so that would work over here because the pressure variation in the vertical column of the tank is is just like a hydrostatic pressure variation, no? Because its area of cross section is uniform. So we can replace the oil layer with a water layer which would apply equivalently the same amount of pressure. So 0.8 into H1 should be the equivalent height of water. And that's what you can see in the formula also finally. Na? It's like a square root 2GH where H is H2 plus 0.8 H1. Yes, Aditya, you have also mentioned the same thing. So that's correct. So you can think of it like a water layer, I mean a water tank with the equivalent height H. And that equivalent height H would be what we have inside that bracket over there, H2 plus relative density of oil into H1. So that's also, especially at an exam level, if you remember this concept, you can directly apply this. So it's something easy to work out. Now, of course, this kind of thing becomes more interesting once we take into account other types of variation in pressure, which can occur because of things like which can occur because of things like accelerated tanks, etc. They can create variations in pressure. So, for example, we could have something like this: that if we have a tank which is inside a vertically accelerated frame, then the efflux velocity is going to change. But remember, the efflux velocity which we'll get will be in the frame of the tank. So the entire kinematics of the liquid that is coming out will be with respect to the tank's frame. So if we assume, for example, the tank is going up at an acceleration a naught, then here the speed of efflux will become square root of 2g plus a naught into h, where h is this. So very interesting example of this is something like this. We have a tubular vessel like this, in which we are rotating this at a very rapid rate of omega naught, let's say. And because of the rotation and the centrifugal force acting on the liquid inside, the liquid is like this. So now as it is rotating, if we open an orifice, what is the speed at which liquid will be flowing out in the frame of the rotating tank with respect to the rotating tank? Now, what is, I mean, typically happening here is that this tube is open from this side. But the reason why the liquid is not flowing out is that we are rotating it with enough angular speed. So the centrifugal force acting on the liquid column is not allowing the liquid to flow out. Okay? So this is of length L. So we have to find the speed of efflux with respect to the rotating tube. Gravity is acting like this. Just try this out, people. So again, consider this to be an orifice. So this one's area is very small compared to the area of cross section of the tube. Yes, very good, Kevin. That's correct. Omega L will be the answer. So interestingly, in the ground frame, the liquid that is coming out will have actually have a horizontal velocity of root 2 omega L, because it will have a component of velocity which is radially outwards, and with respect to ground is already having a tangential velocity of omega L. So in this diagram, in the ground frame, the liquid particles or the volume elements of liquid that are coming out, they'll have a component of velocity into the plane of omega L. Plus, they will have this component of velocity, the efflux velocity, which is radially outwards, which also comes out to be omega L. So basically, here we can visualize the streamlines like this, and we can consider one point, just inside and one point just outside. Okay. Now, because the area of the orifice is very small, so V1 will be negligible compared to V2, because V2 is the efflux velocity, and we have area of the cross section of this is equal to area of cross section of orifice into V2, and E is very small compared to capital A. So with this we have this, okay. But pressure at the point 1 will be equal to, if we take this as the point 0, okay, so it will be atmospheric pressure plus rho omega square L square by 2. Okay. And pressure at the point 2 is P naught, because it's just outside. So P1 plus half rho V square is equal to P2 plus half rho VE square. And again, V is negligible compared to VE. V1 is negligible compared to V. Or another version of something like this is the, like the application of the working principle of a syringe. So there you are creating the pressure difference not by centrifugal force, but by some actual physical force that you are applying on the piston of the syringe. Let's say this is a movable piston. This is of area A. So this is now an orifice of very small area E. It's all filled with liquid. So liquid comes out in a jet like this over here. If we push this with the force of F. So again, you can see if you take this point as point 1 and the point just outside as point 2. So we can see that P1 is P0 plus F by A. This is the principle of Pascal's law. The pressure difference created at any one point is transmitted uniformly to all other points. H1 is equal to H2. P1 is negligible compared to V2 because V2 is the efflux velocity and E is very small compared to calculator. So we have all these various different type of situations. Okay, Vinith, I'm scrolling up. Let me know when you have completed this. Yes, next lecture Ayush will be completely for discussion of doubts, both from module and HC Verma if there's anything. Okay. Because we have completed the theory part altogether of fluid mechanics. So we'll complete the doubts in the next lecture and thereafter we will start with elasticity as the first part of properties of matter. Okay, now a couple of more types of calculation based on this. So next thing is time taken to empty a tank. Through an orifice or an opening. So this is completely an application of calculus, okay? Because we have the speed of efflux, and from that we have the volume rate of outflow as a function of this thing, as a function of the height of liquid in the tank. So it's some general instant of time. If the level of liquid is up to some y or something, if we take it as a variable quantity, then the efflux velocity through an orifice at the bottom is an instantaneous quantity. So the instantaneous value of this speed of efflux. So this is at a general time t, let's say, okay, whereas at t equal to 0, let's say y was equal to h, where h is, okay, so water was filled up to the top. This is an open tank. So in case this is not an open tank and this is vacuumized or something, then you need to apply Bernoulli's equation in a slightly different way. You will not take the surface point as having pressure P naught. You will take it as whatever pressure is given for the air over here. And if it's completely vacuumized, then that pressure will be 0. So it will become slightly different in application. Okay. But here we are considering an open tank as the standard case. Okay. So efflux velocity is instantaneous value at time t equal to t is square root of 2gy. Okay. So therefore volume rate, okay, of outflow, that is efflux velocity into area of cross section. So if we consider the volume of water in the tank as V at this time, so it is area of cross section into Y. Okay, we're using the standard terms that this is of area small a and this area is capital A. So therefore negative of capital dV by dt is equal to small a into root 2 gy. This is our differential equation. Okay. So to find out time taken to empty the tank, we just need to integrate this relation from the initial instant when y was 0 to the final instant when the tank is completely empty. There's no minus sign here. So dy upon root y will become minus a by capital A into square root 2g is a constant into dt. So we'll integrate this from t equal to 0 when y was equal to h to t equal to t when y is equal to 0. Let's say this is some t naught. So t naught is the time taken to empty the tank. So you don't need to memorize the formula we'll get from here. You can just remember the process of how to calculate the So next step, you just complete the integration. 1 by root y's integration will be 2 root y, right? So this will become 2 root gh is equal to a by a into root 2 times g into t. So again, you'll see you'll get an interesting term which is related to the free fall time through a height h, but that multiplied by a factor, which is capital A by small a. So it's much larger time compared to the free fall time through a height h. Okay, so this is what you should get for the time taken to empty the tank. Okay, very good. So final thing before we conclude today's session, as liquid comes out from a tank like this in a situation of efflux, it also applies a reaction force. Okay, so that reaction force can be calculated from the concept of impulse. Okay, so reaction force due to efflux. This is coming out with a speed v. So now you can see that if you visualize this thing as liquid is coming out, dm, the amount of liquid coming out in time dt, is density into area into v dt. Okay, because basically volume rate of flow is a into v. Okay. So, it's the mass of liquid coming out, exiting in time dt. Yes, this. Okay. Now for this mass of liquid that is coming out, the change in momentum and therefore the impulse that that liquid is experiencing because of the pressure difference from inside as it exits is equal to dm into v. Okay. So now the reaction force that that liquid coming out applies is equal and opposite to the rate of change of its own impulse. opposite in direction but equal in magnitude. It is rate of impulse by Newton's third law. So it is equal to dm by dt into v. So the reaction force, so it is density into area into v square, where v is the efflux velocity. Okay, so related to the whole concept of efflux speed, which we calculate from Bernoulli's equation, there are two other types of calculation we can do, which is the time taken to empty the tank, the one we saw before, and the reaction force that the tank experiences because the liquid is coming out from below. So for example, if you place a tank like this on a perfectly frictionless surface, then it is likely to slip backwards because of the reaction force. Or if you place it on a set of rollers and there is friction on the floor to prevent slipping, then the tank will tend to roll back because of the reaction force coming from the liquid, which is gushing out of the tank. Okay, so you will see variations of these type of calculations which will come into play in numerical problems, but with these derivations done in class today, if you review them, you should be able to work out any sort of numerical variation of the calculations. It's not at all a difficult chapter. It's extremely scoring, but then fluid mechanics on its own does not have too much of weightage. Number of questions is less. But at the same time, if you've done it once, you should always look out for fluid mechanics questions in the paper because you're very likely to be able to do them without mistakes. All right, so that's it for today's session, people. Wish you all the best. Yeah, this is like a thrust force only. That's correct, Aman. This is like a thrust force, very similar to what you studied about thrust in rocket propulsion. Yeah, so if there are multiple orifices, then there is multiple forces. Okay, and for example, if the orifices are at different positions on the outer surface of the tank, then the direction of the force can also be different. So there'll be multiple thrust forces which are acting. So their magnitudes and directions could be different. So the net force then becomes a vector sum like that. Hope the point is clear, Amo. Yes. So this topic of fluid mechanics is completed. So please try to finish the questions in the module and the HC Verma, etc. And next chapter we are going to start is going to be properties of matter. So as I told you, we'll be starting with elasticity. So now only doubt solving and questions in fluid mechanics. Okay. So that's it for today's session, people. Wish you all the best. Thanks for attending.